What if empty space isn't really empty? We're taught to think of the vacuum as the absence of everything, a total void. No particles, no energy, just the backdrop for the universe to play out. But quantum physics tells a very different story. According to quantum field theory, even the emptiest vacuum is alive with energy. It teems with fleeting particles, virtual photons constantly appearing and disappearing, like echoes from a deeper layer of reality. This ever present sea of fluctuations is called the quantum vacuum, and it's not just theoretical. It has measurable consequences both in physics and biology. In one of the most astonishing experiments in modern physics, two metal plates placed in a vacuum with no charge, no gravity, and no visible force between them are somehow drawn together by something no one can see. It offers us one of the clearest signs that space itself is not empty and something deeper is going on with the fabric of reality. In classical physics, a vacuum is the absence of matter, pure nothingness. But in quantum field theory, that idea collapses because even when there are no particles, the fields themselves remain. And according to the Heisenberg uncertainty principle, they can never be perfectly still. There's always a baseline jitter, a quantum restlessness that keeps space in motion. Every point in space is filled with what's called zero-point energy, the lowest possible energy a quantum system can have. But unlike the name implies, this energy isn't zero, it fluctuates. These fluctuations give rise to virtual particles, short lived bursts of energy that emerge from the vacuum, interact for the briefest of moments, and then vanish again. They may not be directly observable, but they are essential for understanding how the universe works. In particular, virtual photons, the quantum carriers of electromagnetic force, are constantly appearing and disappearing throughout space. They are what allows charged particles to interact, even across a distance. That means every electromagnetic interaction, from the light in your eyes to the signals in your brain, relies on this invisible sea of activity. In quantum theory, empty space isn't a void. It's a stage full of motion, a restless ocean of invisible energy, always shifting beneath the surface of reality. And if this vacuum field is truly everywhere, then everything we know is built on top of it. Now we ask, if the quantum vacuum is real, if these invisible fluctuations are everywhere, can we measure them? And the answer is yes. In 1948, Dutch physicist Hendrik Casimir proposed a bold experiment. Take two uncharged metal plates, place them extremely close together, and remove all external forces. No charge, no magnetism, just a vacuum. What happens? They move. Slowly but surely, the plates begin to pull towards each other, as if space itself is pressing them together. This phenomenon is known as the Casimir effect, and it's been measured many times since the 1990s with increasing precision. But what causes it? It turns out that fewer virtual photons can exist between the plates than outside of them. That's because the metal surfaces impose boundary conditions, rules that only allow certain wavelengths to exist in the narrow gap between them. Outside the plates, in the open vacuum, a wider range of virtual photon wavelengths are possible. This creates an imbalance in vacuum pressure. More fluctuations are pushing from the outside than within, and that difference pushes the plates together. No classical forces, just the quiet pressure of the quantum vacuum itself. And the best part, this isn't just theory. It's been shown again and again in experiments. The Casimir effect is a direct physical consequence of vacuum fluctuations, and it proves that empty space is not empty at all. So now let's explore why this matters, why the Casimir effect is more than just a clever lab trick. Simply put, it's proof that the vacuum isn't just a background, it's an active player in the game of life, a silent force beneath all matter and energy. And it doesn't stop with metal plates. They may not be directly observable, but they are essential for understanding how the universe works. In particular, virtual photons, the quantum carriers of electromagnetic force, are constantly appearing and disappearing throughout space. They are what allows charged particles to interact, even across a distance. That means every electromagnetic interaction, from the light in your eyes to the signals in your brain, relies on this invisible sea of activity. Other effects like the Lamb shift and spontaneous emission also point to this truth. The vacuum isn't empty. It shapes the way particles behave, the way atoms emit light, and even how matter holds itself together. So, what are we really seeing in the Casimir effect? A rare and subtle glimpse of the vacuum reaching out, its invisible hand made measurable. It's not just an odd force between plates, but a direct encounter with the restless fabric of space itself. And it raises a deeper question. If space has energy, if the vacuum has structure, then might it also have memory? By now, you know the quantum vacuum is real. The Casimir effect proves it. Virtual particles, electromagnetic forces, even the stability of atoms all depend on this ever present invisible field. But what if the vacuum isn't just active? What if it's interactive? Some thinkers, most notably biologist Rupert Sheldrake, have proposed that biological form and memory might be shaped not only by genes or environment, but by something else entirely: morphic fields. These are hypothetical fields of form, pattern, and influence, not made of matter, not even electromagnetic, but possibly operating through principles not yet described by known physics. Yet somehow they are able to guide structure and behavior, especially in living systems. It's a bold idea and highly controversial, which is why I love it. But if such fields did exist, where would they operate? What medium could possibly host something as subtle as a pattern of memory across space and time? Some have speculated that the quantum vacuum could be that medium, that just as it hosts virtual particles and electromagnetic exchange, it might also store or transmit non energetic forms, patterns of organization yet described by physics. Could morphic fields ride the vacuum's fluctuations? Could memory, habit, or form be imprinted, not in matter, but in the structure of space itself? We don't know yet, but the Casimir effect shows us one thing beyond doubt: the vacuum isn't nothing. And if something so invisible can move metal plates, it may be worth asking, what else can it do? We often think of space as a backdrop, a blank canvas where the universe plays out. But the quantum vacuum reminds us it's more than that. It's dynamic, it's structured, it's capable of shaping physical reality in subtle, measurable ways. From the forces between particles to the quiet push of the Casimir effect, space itself has agency. We don't know yet how far that agency extends, whether it's just a field of fluctuations or something deeper, whether it holds only energy or possibly memory. But in the coming years, as science continues to probe the vacuum and thinkers explore its implications, we may find that the most mysterious part of reality was never hidden, just overlooked. Thanks for joining me in exploring the hidden structure beneath everything. Let me know in the comments what you thought. And if you enjoyed this, be sure to subscribe, hit the like button, and most importantly, hit the notification bell. That way, the next time Biolumination releases a video, you'll be there to join the journey. Until next time, take care.